Hello everyone, myself Shweta Shah, Assistant Professor at L.J. Institute of Engineering and Technology, Ahmedabad. We are here for the subject Computer Organization and Architecture. We have started Unit 5, that is Central Processing Unit. In this unit, in last session, we have seen stack organization. In this session, we are going to see general register organization and instruction format. Let me start with general register organization. First, we see what is general register organization. In the programming example in last chapter, what we have seen, we have used memory locations to store your pointers, counters, return address, temporary result, or partial product, etc. Like so, this is the most time consuming task for any digital system that you access memory. Okay, so instead of this, our system will be more efficient if we store this intermediate values into processor register instead of storing into memory. Okay, so to do this, we will require large number of registers that should be included into your CPU, and the most efficient connection between them will require to complete this task. Okay, the register can communicate to each other not only for this direct transfer but also for your but also for performing your micro operations. Okay, so by this way, that means we require many number of registers and to provide some path between them. This is our task for organizing this general purpose registers. Okay, so let me see how you can do this. For example, we can consider a system which has a 7 registers, and how you can connect this 7 resistor through ALU by some kind of this circuit. Okay, let me see how the circuit is organized. The output of each resistor is connected to two mux, that is known as mux A and mux B. Okay, and this output of this mux is connected to ALU via bus A or via bus B. So data from any of this resistor can be selected by the select A and select B and stored into this mux A and mux B, and after that your operation is provided over from here by this control operation control that will tell the ALU which operation is going to be done on the data which is available on bus A and bus B. Okay, so your operation will be done on the content of bus A and bus B, which is ultimately a content of your resistor, and that is going to be performed in ALU, and the output is going to be generated in output, and that is going to be stored into all of this because we have connected this output to all of this resistor. Okay, so output is available at input of each and every resistor, but that is going to be stored into only that resistor which you have selected by SELD. Okay, so by providing this 3-bit control, you will select any of one resistor, and only of that resistor's input is going to be activated, and the data which is available in this bus is going to be stored into that resistor. Okay, here we have shown line, simple line, but actually it is a bus, 8-bit bus that is connected to each and every mux. Okay, so by this way you can connect your general purpose resistor. Okay, for limitation here we have used only 7 resistor. Let me see how you can provide this control, how you can select this mux, which resistors content will available in mux A, or which resistors content will available in mux 2, or you can say mux B, and output is going to be stored where, and which operation is going to be performed. How you can decide this? So to decide this, all of these things, you will require some control word. How this control word can be generated, let me see with one example of micro operation. For example, let me have to do micro operation of R1 given R2 plus R3. That means the content of resistor R2 and R3 is going to be added, and the result is going to be stored into resistor R1. Okay, so what we will require, mux A should select resistor R2, mux B should select resistor R3, and our operation we have to provide over is of addition. third task, and the output is going to be generated over here, and that is going to be stored into register R1. So for that we have to provide selection over here to store this content into register R1. Okay, so our main task is selecting input for mux A, mux B, and for operation of ALU, and selection for this 3 to 8 decoder, select D. Okay, so how we can do, we have to select this, select A to select this mux, select B to select this mux input, operation, which operation is going to be done, and select D to select output is going to be stored where. Okay, so how, let me see how our control word is going to be stored. This is like this, it is of 14-bit register, you can say as a register, or you can say 14-bit pattern, that is going to be stored as, that is going to be stored as like this. First 3-bit will denote select A, next 3-bit will denote select B, next 3-bit will denote select D, and next 5-bit will denote operation. Okay, so first will show your select A, second will show your select B, third will show your select D, and last 5-bit will show operation. Okay, and for that bit pattern is already decided. If you want to select register R1, you have to use select A as a 001. If you want to select register R2, you have to use 010. If R3, then 011. So by using this, any register you can use in a micro operation. Address of that register you have to use for this 3 bits selection of selection A, B, C. Sorry, A, B, and D. Okay, here for 00 code you are using input from input register. Okay, and next 5-bit will denote your operation, and these operations are listed over here. If your 000 all bits are 0, that means your operation is going to be performed is of transfer A. If 00001, then you will do increment A operation. If it is 00010, then you do addition, and so on. Okay, so by this method you have to calculate, you have to generate this 14-bit pattern, and that is going to be your control word, and this control word should be provided by control unit at every starting of your cycle. Okay, at every starting of your cycle, this control word should be provided by your CPU. Okay, for example, that we have seen already, that we are adding R2 and R3's content and going to store result in R1 register. So how you can represent this? Your select A will be R2, select B will be R3, select D where you are storing your result is R1, and your operation is of addition. So let me see how will be your bit pattern. For R2 you have pattern 010, for R3 you have 011, for R1 storing your result the pattern is 001, and for your operation of add, what is your pattern? That is 00010. So this is your 14-bit pattern that is provided by control unit in the starting of each and every cycle. For example, you can say that this control will be available to add this number. By this way, any of operation can be done. For example, if your operation is of like subtraction, right? You are doing subtraction of content of R2 register and R3 register and going to storing this result into R1 register. So how you can represent this? By your selection A will be R2, selection B will be R3, selection D will be R1. That is same. But your operation is going to be subtraction. For subtraction, you have operation as a 00101. That is 00101. Okay. So by this way, your 14-bit selection for this micro operation of subtraction is like this. And so on. For any of this listed operation, you can generate this kind of 14-bit binary pattern, and that should be available at starting of each and every cycles. Okay, so this is your register organization, how you can organize this register. In this example, we have seen only 8 register, but it is possible that you have large number of register and with larger sizes. Okay, this is also possible. For that you will require larger size mux and decode. Okay, so this is your register organization. Next, let me see what is instruction format, how you will format your instruction. That means in your instruction which bit represents what. Okay, so the format of instruction is usually depicted in a rectangular box symbolizing the bits of instruction as they appear in memory word or in control register. The bits of instruction are divided into a groups called as a field, and the most common groups or fields are as given. First one is an operation code, which will define which operation is going to be done. Second field is an address field, which will designate a memory address or a processor register address on when where your data, where your operand is stored. And third field is a mode field that specifies the way the operand or effective address is determined. For example, you have used indirect addressing. Okay, so which mode you have represented your operand. In short, we can say first one is your opcode, second one is your operand, and third one is mode, which will determine how you will represent, how you will use your operand, or your whether your operand is address, whether your operand is data, or whether your operand is indirect address. What is your operand? Okay, that is represented by this mode field. Okay, so this will be your instructions format. Let me see how this general categories of this instruction that are divided majorly into 5 parts: 3 address instruction, 2 address instruction, 1 address instruction, 0 address instruction, and risk address instruction. So what is this 3 address instruction, 2 address instruction? These are your number of operands. Okay, for example, if you say your instruction is a 3 address instruction, that means your operand is represented by 3 field. Okay, by 3 field. In 2 address instruction, your operand is represented by 2 fields. In 1 address, by 1 field. We will see further in details how it is represented. Okay, for example, we will see this all type of instruction for one simple same program, that is you are going to generate x is equals to a plus b into c plus d. Here a, b, c, d and x are your memory locations. Okay, so you are going to do what? You are going to add the memory content of a location and b location, then of c location and d location, and the result of this both addition is going to be multiplied. Okay, and going to be stored at location x. To do this task, here what task we will require? We will require addition, multiplication, division. Here we don't require division, but for example, if in any task you require division operation, so we will represent this by add, SUH for subtraction, MUL for multiplication, DIV for division. For loading some number, loading content of memory to some register, we will use load operation code. For storing, we will use store operation code. Okay, and for accumulator we will use. So we are ending our session over here. In next session we will see this instruction formats in further details.